So here we start another chapter. This is called Generalized Additive Manufacturing Process Chain. In this process chain, as we have discussed briefly at the beginning of the semester, in the previous week, there are several steps in this chain, and in this chapter we will be discussing many of the details of this pipeline, the design and fabrication pipeline. Yes, I think you remember this image. We have 8 main steps: designing, STL conversion. There's a mesh file for intermediate language, if you remember, in order to easily transfer all these models into various additive manufacturing machinery. We need to convert them into an STL file, then transfer it to the CAM software, do settings, print it, remove it, do some post-processing, remove support structure, do some cutting, let's say, and then use it in your application. So now let's focus on the first one, the conceptualization or the CAD modeling. As you know, we have many software, many different CAD software, and we are using this software to obtain a digital form. And since this is a digital manufacturing system, digital manufacturing process, we need to have the digital model of your design. And obviously, additive manufacturing couldn't be developed actually if we didn't have any CAD system. Without CAD systems, we cannot talk about additive manufacturing. And the advantage actually that additive manufacturing is that once you design your part, then there will be no intervention of any other things between your design and the fabrication stage. But if you consider the conventional approaches, you need to modify your design according to the conventional rules for design for manufacturing. But in the design for additive manufacturing, we have less rules, so we have little intervention between the design and fabrication stages. And another important issue in terms of CAD systems, CAD software, is that we need to have watertight models while designing our parts. Otherwise, once you do the conversions into STL files or different mesh file formats, you will have problems in the slicing. And once you have these problems, you can use some STL fixing software like NetFab or different mesh mixer. There are such STL fixing software, but if your CAD system, CAD software is powerful, then the result of your conversion should be a watertight model. So anyone have questions on the first step? Since you are already familiar with the fundamentals of CAD, how you design, there are many tools. By using these tools, you can design anything. Instead, actually, if you don't want to design, you may simply do some scanning operation, 3D scanning, and try to obtain the CAD models of the available products. This is also possible. Once you do scanning, then you can directly start from the second step, not from the first one, since in scanning, most of the scanners actually output STL files or mesh files. You can directly start from this second step. Instead of STL files, these days you also have another format. This is called as additive manufacturing file format, but it's not finalized yet. There are organizations, standard organizations like ASTM and ISO are working on this format, additive manufacturing file format, and they are trying to add more properties into these formats. Since in the STL format, which is actually the abbreviation of stereolithography, ST, stereo, lithography, this L comes from lithography. And the problem is that in the STL files, we only have the information of triangles, the vertices of the triangles and the normal of the triangles. So we don't have any information about the construction data, how we design this part, or we don't have information about the color, about the assembly. We only have information about the outer profile of the model. This is the biggest actually problem with the STL file format. And we have triangles on the outer surface, and if you have, let's say, conform surfaces, we cannot model them with STL files. Since STL file is an approximation, you need to represent the same surface with triangles. So it's another problem of using STL files. And you can decrease the size of your STL files by setting the size of the triangles. If you have larger triangles, then the size of your final file will be low, but the resolution will be worse. So if you want to increase the resolution of your file, then you need to have many triangles. But now the problem is that the size of your file, the STL file, will be too much. Maybe sometimes around some gigabytes, but usually it will be around some megabytes. So in summary, once you decrease the size of the triangle, the size of your file will be increased, but the resolution will be better. And if you increase the size of the triangles, the number of triangles will always be decreased, and the size of your STL file will be smaller. There's a question about the formats. What do you mean by BDF format? I don't know anything about BDF format. So let's continue with the slides. Yes, this is an important issue about the STL files. We said that in the STL files we have many triangles, but the order of its triangles is not important. So assume that you have such a box-like shape. You have two triangles on this surface, but one triangle may be represented at the top of the file, and the other triangle may be at the bottom of your file. It doesn't matter, since this is just representing the whole surface, so the order is not important. The CAD software, which is importing the STL files inside, they all try to decode this STL file and represent with the whole model. So the in order of the triangles are not important. So another, as I mentioned, we don't have any color information inside. We don't have material information, another feature information, tolerances. Nothing is stored in the STL files. Just measure, just the information about the triangles we have. And there is also no units. You don't have unit information, but for most of the time, we assume that the unit is in millimeters. If you want to have a unit in inches or meters, then you should do some modifications in your CAD software or in other manufacturing software. And since we have these difficulties in the STL file, these problems, that's why people are working on another format, additive manufacturing file format. And in that format, they want to include such information: the color of the product, the unit, the material of the product, and also sometimes the design history. How you design it, you do first extrusion and then do cutting, do some joining operations, subtraction operations. These will be stored in the additive manufacturing file format. Another thing, they are trying to come up with a file format which is universal for all the additive manufacturing processes. The format shouldn't be just working with a single operation, just maybe fused plant fabrication or stereolithography. It should work with any additive manufacturing method. This is one of the motivations of the additive manufacturing file format. But still these days, we have this problem. STL is still a de facto standard. Any questions, guys, about the conversion to an STL file? So then what we do, this third step is not that complicated. Once you have the STL file, a proper STL file, a watertight STL model, then we simply transfer it to the AM machine, or we can say that we are transferring to the CAD software of the AM machine. And then what we do, as I have shown you while discussing the basics of Cura, we do some scaling, for instance. We can rotate it on the table, we can orient it, we can add some little features, we can increase the number of products on the table, so we can mirror them, multiply them. So these are all possible, and we can do them on the CAD software. You see, you can print multiple times on the same table. And this is actually a nice property of STL files. You can easily scale them. Since we have a unitless file, you can easily add units to it and simply multiply the values of the coordinates, and you can have the scaled versions of your design easily. And in some cases, for instance, you design a product having a size of 50 millimeters, but your CAD software might be aware of the shrinkage problem in your fabrication step. So that's why it performs some enlarging operations without showing you the details, since at the end of the fabrication process, it doesn't want to give you a larger product or a smaller one. This is done actually inside of your CAD software, to eliminate the shrinkage problem or give you some, let's say, volume for the coating operation. And in some other CAD software, we also have some further, let's say, features. For instance, you may add some letters onto your design, or you may add some textures. So this can be done inside the CAD software. Another thing you can do, if your design is a large one, but the build volume might be smaller, so what you do in that CAD software, you divide your part into smaller segments. With the help of this approach, you can print them separately, and then later, once all the parts are printed, you can join them by using some, let's say, glue-like things and have the final product. Or instead of segmentation, you may import smaller parts into that CAD software and try to join them in that software. Instead of doing these operations on the CAD side, you can perform these operations on the CAM, let's say, software of additive manufacturing system. Any questions, guys? Okay, let's jump to the fourth step. This is machine setup, and I made you a demo about this machine setup last week while we were playing with Cura. So the machine setup is mostly done on the CAM software. You need to adjust the settings. We have many parameters. We have the layer thickness. We have different materials, and some of the parameters depend on the material properties. So you should first check the material and then adjust other parameters. And you may also have some default parameters for specific ones. So you don't need to spend much time on it. By simply selecting the appropriate material, your CAM software will arrange the other parameters. And you may have some, obviously, metal powders depending on the type of metal powder you are using. In some, especially metal systems, you need to do parameter optimization, especially if you are using a new, let's say, alloy or new metal powder. You need to work on parameters, maybe for some days, some months, to find the optimum parameters, optimum laser power, focus diameter, the thickness, the gap between the lines actually while you are filling the interior of the parts. But there are many parameters to work on. So once you have an incorrect setup, obviously the quality of your part will be worse, and you may need to rerun all these steps and try to fabricate another example. And obviously, before starting the manufacturing, you may need to do some physical preparations. You need to adjust the level of your plate. You need to clean the nozzle, maybe clean the table. So these are things actually you need to do physically before starting the fabrication. Yes, your material may be finished, so you need to have new, let's say, bunch of material, new cartridge of material, new tank of material, depending on your fabrication process. You need to do these operations. And in some cases, if you are in high quality system, some of these steps are automated, but some primitive ones are not automated. You need to load your material yourself or unload it yourself, but in professional ones and expensive ones, we have mostly automated systems. Now let's call it a day and stop here. I will continue with this chapter on Tuesday. And if you have questions, you can ask now. If you don't have any, you can call it a day and say goodbye.